Hello, everyone. We are the Neuro Netflix and Chillers, and our project is on early detection of Parkinson's disease through voice recognition using machine learning.
Hi, I'm Brendan Istvan,
I'm Dan Tran.
I'm Fong Lei.
and we're the developers that are going to end Parkinson's.
Imagine if the simple sound of your voice could reveal the earliest signs of a disease. Parkinson's disease is a progressive neurological disorder that affects movement, muscle control, and speech. It impacts millions globally, and here in Virginia, the threat is especially real. According to the CDC, Virginia ranks among the states with the highest mortality rates for Parkinson's, with over 1,000 deaths reported in 2022 alone. Our project began with a question: can machine learning detect Parkinson's just from how someone speaks before traditional clinical signs ever appear?
Today, diagnosing Parkinson's often means waiting for visible symptoms: tremors, stiffness, impaired motor control. But these often appear late when treatment is less effective. Voice, on the other hand, changes early. Subtle pitch tremors, increased breathing, reduced vocal intensity, early warnings hiding right in plain sound. This inspired us to explore a more accessible, non invasive path: machine learning analysis of vocal biomarkers.
For our dataset, we used a publicly available dataset from the University of California, Irvine that contains voice recordings of individuals with and without Parkinson's. From these sustained vowel sounds, researchers extracted 22 key vocal features, things like jitter, which measures tiny pitch fluctuations, shimmer, which tracks amplitude variations, and noise to harmonic ratio, a measure of breathiness or hoarseness in speech. We then cleaned the dataset, removed non-formative columns like name, and ensured there were no missing values. Then we applied standard scaling to normalize the features across the dataset, which helped models treat all variables equally during training. Additionally, to improve model performance, we engineered new features that capture deeper vocal patterns. We combined relative measures like jitter and shimmer into composite scores, calculated pitch ratios, applied log and power transformations, and created interaction terms. We also used PCA and kernel PCA to reduce noise and highlight the most informative patterns. Altogether, these engineered features gave our models a richer, more structured view of the voice, making subtle signs of Parkinson's easier to detect.
Once our data was ready, we trained a range of machine learning models to detect Parkinson's disease from voice recordings. We use classic models like logistic regression, support vector machines, and k nearest neighbors, as well as more advanced methods like random forests, bagging, boosting, and ensemble. Each model acted as a binary classifier, asking one simple question: does this voice suggest Parkinson's disease? Across the board, feature engineering improved performance. For example, our bagging model improved from 93.9% to 95.4% accuracy after feature enhancement, capturing more subtle vocal signals. These results show the power of both smart algorithms and smart data. Together, they made detection more accurate and more possible.
This project showed us how powerful and challenging it can be to apply AI to healthcare. The human voice holds so much information, yet decoding it requires careful data handling, model design, and constant iteration. We learned that the journey from raw data to meaningful insight isn't linear, as it requires exploration, failure, and refinement. But in the end, we took a meaningful step towards a tool that could one day assist doctors, support early diagnosis, and change lives, all from just a few seconds of sound. In a world where early detection can change everything, our voices may be telling us more than what we think. This project is one step towards giving them a louder voice in a fight against Parkinson's.
This project taught us that successful machine learning isn't just about choosing the right model, it's about how you shape and tune every part of the pipeline. When our early results fell short, we explored feature engineering to better represent the data and used techniques like grid search to systematically tune hyperparameters for each model. This process helped us understand how small changes, like adjusting the number of trees in a random forest or the kernel type in an SVM, can significantly affect performance. It also highlighted the importance of validation strategies and careful experimentation in producing reliable results. Through this, we developed a stronger appreciation for the balance between model complexity, interpretability, and generalization.